Tonight we're exploring one of the strangest questions in all of physics, whether time is truly real. First though, a brief and honest word. You've probably noticed there are no ads on these videos, so nothing will break the quiet tonight. Keeping it that way does take a little help though, and the best way to lend it is the ebook. If you have a spare minute, and only if you do, pause here and take a look. There's a QR code on screen throughout, and a link down in the description across to the website thesleepyscientist.com. It's an unhurried, patient guide to quantum physics, the ideas behind these videos given a little more room to breathe, with a full narrated audiobook alongside. Honestly, a quiet look really is the most helpful thing you can do to keep these videos coming. That's all I'll ask tonight, and I ask it warmly. Thank you. Now before we begin, let me know where in the world you're watching from and what time it is for you. It seems obvious at first. The past is behind us, the future is ahead, and the present is where reality happens. But the deeper physics goes, the stranger time becomes. It bends with gravity, stretches with motion, points one way through entropy, and may even vanish from the deepest equations of quantum gravity. So get comfortable, let the clocks do whatever mysterious thing clocks are doing, and let's begin with the time we feel before we ever try to measure it. Before physics ever built its great clocks, time was already there in the most intimate way possible, not as a number, not as a dial, not as a line in an equation. Time first appears to us as experience. It is the feeling that life is moving, that the present is opening in front of us and closing behind us, that one moment is arriving while another is slipping away. We do not need a laboratory to feel this. We feel it in waiting, in remembering, in growing older, in hearing a song end, in watching daylight fade from a room, or in realizing that a cup of tea has gone cold while we were thinking about something else. Everyday time feels obvious. It feels continuous, as if reality is gently flowing from one moment into the next. It feels universal, as if the same now stretches across every room, every city, every planet, and every star. It feels so natural that asking whether time is real can sound almost silly at first. Of course time is real. We wake up in it, we move through it, we lose it, waste it, measure it, chase it, and occasionally spend far too much of it wondering where we put our keys. But the time we feel is not yet the time of physics. Human time has texture. It stretches and contracts. 5 minutes can seem almost endless when we are waiting for important news. A whole afternoon can vanish when we are absorbed in something pleasant. Childhood summers can feel enormous in memory, while a routine week can pass so quietly that it leaves almost no trace. The clock may treat each second as equal, but consciousness does not always behave like a clock. The mind does not simply record time, it shapes it. This is the first important separation. Experienced time is the time of memory, attention, expectation, and awareness. Physical time is the time measured by clocks, used in equations, and tested through motion, light, gravity, atoms, and energy. These two kinds of time are connected, but they are not identical, and many of the deepest disagreements about whether time is real begin right here, in the gap between the time we live and the time physics describes. The human experience of time has a direction. We remember the past, but we do not remember the future. We anticipate tomorrow, but we do not anticipate yesterday. We see causes before effects. A glass falls, hits the floor, and breaks. We do not see broken pieces calmly leap together, rebuild the glass, and return it to the table, although that would be a useful feature in kitchens. We grow older rather than younger. Scars form after wounds. Footprints appear after someone walks across sand. This is the psychological arrow of time, the inward sense that life points one way. Memory is central to this arrow. The past feels real to us partly because it has left records. Those records may be inside the brain, or written in photographs, books, fossils, tree rings, ruins, and starlight. The future does not contain records in the same way. It appears as possibility, not as memory. So our minds arrange reality into a deeply familiar structure: what has happened, what is happening, and what may happen. Modern neuroscience suggests that this structure is not passively received. The brain actively builds a stable sense of sequence from changing information. It combines sight, sound, touch, body signals, memory, and expectation into a coherent flow. Different parts of the nervous system contribute to timing at different scales, from tiny fractions of a second to longer rhythms of attention, habit, sleep, and aging. There does not seem to be one tiny master clock in the brain, sitting somewhere behind the eyes and politely announcing each moment as it arrives. Instead, the sense of time is constructed from many processes working together. Researchers such as Carl Friston have argued that the brain is deeply predictive. In predictive processing, the brain is not merely waiting for information from the world. It is constantly generating expectations and comparing them with incoming signals. This matters for time because experience depends not only on what is happening now, but on what the brain expected to happen, what it remembers happening, and how it updates its picture of the world. Conscious time is therefore partly a story of prediction, correction, and continuity. That does not mean time is imaginary. A constructed experience can still correspond to something real. Colour is constructed by the brain from light of different wavelengths, but light is not fake. Sound is constructed from pressure waves interpreted by the auditory system, but pressure waves are real. In the same careful way, the flow of time may be a feature of conscious experience built from physical processes, even if physics later shows that time itself is not a simple flowing substance. This distinction is crucial. When physicists disagree about whether time is real, they're usually not denying that we experience time. They're asking what that experience corresponds to in the structure of nature. Is the flowing present a basic feature of the universe, or is it something produced by brains moving through a world governed by deeper laws? Is the future genuinely open, or is it part of a larger space-time structure we cannot perceive all at once? Is time fundamental, or does it emerge from change, entropy, causality, and information? The ordinary feeling of time cannot answer those questions by itself. It gives us the starting point, not the conclusion. It tells us that time is real in experience, but not whether time is fundamental in physics. It tells us that the present feels special, but not whether the universe agrees. It tells us that life seems to move forward, but not yet why forward exists. So before equations enter the story, time already has two faces. One is intimate, flowing, and psychological. The other waits to be made precise through clocks, motion, and mathematical law. Physics begins by taking the time we feel so naturally and asking whether it can be measured exactly, described universally, and placed into the machinery of nature. That was the first great ambition, to turn the private river of experience into a public clock for the cosmos. For a long time, physics treated time as the one thing everyone could agree on. Objects might move in complicated ways, planets might wander across the night sky, apples might fall from trees with suspiciously good timing. But beneath all of this motion, there seemed to be a steady background rhythm. Time was imagined as something that flowed evenly everywhere, whether anyone noticed it or not. It did not depend on a clock. It did not depend on a person watching. It did not depend on whether the universe was busy doing something dramatic or quietly minding its own business. This picture reached its most powerful form in the work of Isaac Newton. In the 17th century, Newton gave physics a structure so successful that it shaped scientific thought for more than 200 years. His great work, Philosophiae Naturalis Principia Mathematica, usually called the Principia, was published in 1687. It set out the laws of motion and universal gravitation, and it showed that the same mathematical principles could describe both ordinary objects on Earth and the movement of worlds in space. This was a profound unification. A falling stone, a cannonball, the moon, and the planets could all be understood within the same framework. The heavens were no longer a separate realm, obeying mysterious celestial rules. They were part of the same physical universe as everything else. Newton's physics made nature feel like a vast clockwork system, elegant, predictable, and deeply mathematical. At the centre of that clockwork universe was absolute time. Newton described true mathematical time as something that flows uniformly, without relation to anything external. In simpler words, time existed on its own. It passed at the same rate everywhere. It did not matter whether objects moved or stayed still. It did not matter whether the universe contained clocks, planets, people, or a single, very patient rock. Time itself would continue to flow evenly in the background. This is close to how time feels in everyday life. We imagine that there is one shared now, one universal ticking, one hidden cosmic rhythm that all clocks are trying to follow. Some clocks are better than others, of course. A modern atomic clock is rather more reliable than a kitchen clock with a weak battery, and both are more useful than guessing the time from how tired you feel, which is a brave but dangerous method. Still, we usually assume they are all measuring one underlying thing. Newton turned that assumption into a foundation for physics. In Newtonian mechanics, time is what allows motion to be described mathematically. An object has a position at a particular moment. Its velocity describes how that position changes with time. Its acceleration describes how velocity changes with time. Forces explain why acceleration happens. This gives physics a clean structure. Where is the object now? How is it moving? And where will it be later? Newton's second law made this especially clear. In spoken form, the central idea is force is equal to mass multiplied by acceleration. Acceleration means a change in motion over time, so time is not just decoration in Newton's physics. It is built into the basic description of motion itself. Gravity also depended on this universal background. Newton's law of universal gravitation said that every mass attracts every other mass, with a strength depending on the masses involved and the distance between them. In spoken form, the idea is the gravitational force between two objects is proportional to the product of their masses and inversely proportional to the square of the distance between them. With this law, Newton could explain why planets orbit the Sun, why the Moon falls around Earth instead of flying away, and why objects near Earth fall downward when unsupported. All of this required a reliable time parameter. The planets could be tracked from one moment to the next. A falling object could be predicted after 1 second, 2 seconds, or 10 seconds. The motion of the solar system could be treated as an evolving mechanical pattern. If the positions and motions of objects were known at one time, the laws could be used to calculate their future motion. This is why Newton's universe is often called clockwork. It suggested a cosmos that ran according to fixed laws, with time ticking steadily beneath the entire machine. The universe might be unimaginably large, but in principle it was orderly. Given enough information and enough mathematical skill, the future could be predicted from the present, and the past could be reconstructed from what exists now. In this view, time is real in a very strong sense. It is not merely what clocks measure. It is not just something the mind invents to organize experience. It is part of the deeper architecture of classical physics. It is the stage on which matter moves, forces act, and the universe unfolds. But even in Newton's own era, not everyone agreed. Gottfried Wilhelm Leibniz, the German mathematician and philosopher, argued against the idea of absolute time. Leibniz thought time was relational. For him, time was not an independent thing that existed by itself. It was the order of events and changes. Time described relationships, one event before another, one process after another, one motion alongside another. The difference is subtle, but enormous. Imagine a ticking clock in an otherwise empty room. Newton could say that the clock measures time because time is passing independently in the background. The clock is simply marking something that already exists. Leibniz would say that what we call time is found in the changing states of the clock itself, one tick after another, one position of the mechanism after another, one event followed by the next. Now imagine an entirely empty universe. No matter, no light, no clocks, no motion, no temperature, no particles, no events, no changes at all. For Newton, time could still pass in that empty universe. Absolute time would continue flowing, even with nothing inside it. For Leibniz, this made no sense. If absolutely nothing changes, if there are no events to order, then there is no meaningful time. Time is not a container sitting there empty. Time is the relationship between things that happen. This debate still echoes through physics. Is time like a stage on which events occur, or is it only the ordering of the events themselves? Is it a thing in its own right, or a pattern of change? Does the universe need time before anything can happen, or does time appear because things happen? Newton's view became the practical foundation of classical physics because it worked astonishingly well. It helped explain projectiles, tides, machines, falling bodies, planetary orbits, and the motion of comets. For ordinary speeds and ordinary gravitational fields, it still works beautifully today. Engineers and astronomers still use Newtonian ideas when the conditions are suitable, because a good approximation is not a failure. It is one of physics' favourite tools. But classical success did not settle the deeper question. Newton gave physics an absolute clock. Leibniz asked whether the clock was only meaningful because things changed. For centuries, Newton's picture seemed almost unbeatable. Then physicists began to study heat, disorder, and irreversible change. And slowly, the perfect clockwork universe began to reveal a new problem. If time flows evenly in the background, why does the world itself seem to move so strongly in only one direction? The clockwork universe was beautiful, but it had a problem hiding in plain sight. The problem was not that things changed. Newton's physics was excellent at describing change. It could follow a falling object, a swinging pendulum, a planet in orbit, or a comet returning after a long journey through the dark. The deeper problem was that ordinary change seems to have a direction. The world does not merely move. It appears to move one way. A hot cup of tea cools on a table. It does not become hotter while the room politely gives up some of its warmth. A dropped glass breaks into pieces. The pieces do not suddenly slide together, rebuild themselves and leap back into your hand, which would be convenient, although slightly alarming. Smoke spreads through a room. It does not gather itself neatly back into the end of a match. A drop of ink spreads through water. It does not unmix into a perfect dark bead again. Stars burn their nuclear fuel. Bodies age. Batteries run down. Perfume drifts through air. Milk poured into coffee swirls into pale brown clouds and then blends, rather than carefully separating itself later because it has reconsidered. This one-way behaviour is called the thermodynamic arrow of time. It is the direction in which heat spreads. energy becomes less concentrated, and many everyday processes become effectively irreversible. It is not the only arrow of time we experience. There is also the psychological arrow, where we remember the past and anticipate the future. There is a causal arrow, where causes seem to come before effects. But the thermodynamic arrow is one of the deepest physical clues because it connects the direction of time to heat, probability, and the structure of matter. The key concept is entropy. Rudolf Clausius introduced entropy in the 19th century while developing the science of thermodynamics. Thermodynamics began as the study of heat, work, engines, and energy, but it quickly became something much deeper. Clausius helped formulate the second law of thermodynamics, which says in broad terms that in an isolated system, entropy tends to increase. Entropy is often described as disorder, but that word can be misleading. Disorder makes entropy sound like the universe is judging your bedroom, which is unfair because the universe has many other things to worry about. More carefully, entropy is related to the number of microscopic arrangements that can produce the same large-scale state. A simple example helps. Imagine a gas in a box. If all the gas molecules are packed into one tiny corner, that is a very special arrangement. There are relatively few ways for all the molecules to be gathered together like that. But if the gas is spread evenly throughout the box, there are enormously more ways for the molecules to be arranged while still looking, on a large scale, like an evenly spread gas. The spread out state has higher entropy because many more microscopic configurations correspond to it. This is where Ludwig Boltzmann enters the story. Boltzmann developed statistical mechanics, the bridge between the motion of individual atoms and molecules and the large-scale behaviour of heat, pressure, and entropy. He showed that the second law of thermodynamics is not simply a mechanical commandment forcing every particle to behave in one direction. It is a statement about overwhelming probability. A gas spreads through a room because there are vastly more ways for its molecules to be spread out than clustered in one corner. Heat flows from a hot object to a colder one because there are vastly more ways for energy to be shared around than to remain neatly concentrated. A broken glass stays broken because there are far more ways for its fragments, sound, heat, and surrounding air to be in a scattered state than in the extremely precise arrangement of an intact glass sitting peacefully on a table. So when entropy increases, reality is usually moving from rare, special arrangements toward common, more probable arrangements. Josiah Willard Gibbs developed another powerful way to describe this kind of physics. Instead of trying to follow every single particle in an enormous system, Gibbs used statistical descriptions of large collections of possible states. This was essential because even a tiny sample of gas contains an absurd number of molecules. Tracking every particle individually would be hopeless in practice. Statistical mechanics allows physicists to describe the behaviour of the whole system without needing a microscopic diary for every atom. This is where time becomes strange again. The large-scale world clearly has a direction. Tea cools, smoke spreads, stars age. But many microscopic laws of classical mechanics work both forward and backward in time. If you imagine a few ideal particles moving and colliding, the reversed motion can still obey Newton's laws. The equations do not always come with a little arrow printed on them saying this way to the future. That creates a puzzle. If the microscopic laws are mostly time-symmetric, why is everyday experience so time-asymmetric? Why do we see glasses break but not unbreak? Why do gases spread but not spontaneously gather? Why does the universe appear to remember one direction and not the other? This question was sharpened by the Loschmidt paradox, named after Joseph Loschmidt. He pointed out that if the motions of particles could be reversed, then a system that had been increasing in entropy should be able to run backward and decrease in entropy. If the underlying laws allow both directions, where does the one-way arrow come from? The answer is subtle. The reverse process is not impossible in the simplest mathematical sense. It is just fantastically unlikely. To make a broken glass reassemble, every tiny piece, vibration, air molecule, and bit of heat would need to move in an extraordinarily precise coordinated way. The laws may permit such a reversal, but the required arrangement is so special that nature does not stumble into it under ordinary conditions. This means the arrow of time may not come from time itself as a flowing substance. It may come from probability, entropy, and the fact that the universe began in a very special low entropy state. The past was more ordered in a precise statistical sense. The future is the direction in which there are more possible microscopic arrangements available, and this brings us back to the question of whether time is real. If time is real, one of its most obvious features seems to be direction. We do not experience life as a neutral line that can be travelled both ways. We experience it as a one-way unfolding. Yet physics struggles to explain whether that direction belongs to time itself, or whether it emerges from matter, energy, probability, and the early condition of the cosmos. The clock still ticks forward. But now the ticking is not enough. The world has an arrow, and that arrow seems to be made not from time alone, but from heat, statistics, and the quiet mathematics of things becoming more likely. And the mystery becomes even sharper when Einstein removes the idea of one universal cosmic clock altogether. The next great break in the story of time came from light, not from clocks directly, not from aging, heat, or broken glasses. From light, moving through empty space with a speed that refused to behave like ordinary speeds. It was this refusal that quietly began to dismantle Newton's universal clock. In the 19th century, James Clerk Maxwell brought electricity and magnetism together into one theory: electromagnetism. Before Maxwell, electric and magnetic effects had often been treated as related but distinct phenomena. Maxwell's equations showed that they were deeply connected. A changing electric field could produce a magnetic field, and a changing magnetic field could produce an electric field. Together, these changing fields could travel as a wave. When Maxwell calculated the speed of those electromagnetic waves, the value matched the known speed of light. This was a profound discovery. Light was not just something that helped us see things before bumping into them in the dark. Light was an electromagnetic wave. But this created a problem. Waves usually seem to need a medium. Sound travels through air. Ripples travel through water. So physicists assumed that light must travel through some invisible substance filling space. They called it the luminiferous ether. This ether was imagined as a kind of hidden cosmic medium, the thing light waved through as it crossed the universe. If the ether existed, Earth should be moving through it as it orbited the Sun. And if Earth moved through it, then light should appear to travel at slightly different speeds depending on its direction. Light moving with Earth's motion through the ether should behave differently from light moving against it, or sideways through it. In 1887, Albert Michelson and Edward Morley tested this idea in one of the most famous experiments in physics. Their Michelson-Morley experiment used an interferometer, a device that split a beam of light into two paths and then recombined it. If light travelled at different speeds in different directions because of Earth's motion through the ether, the experiment should have revealed a tiny shift in the interference pattern. But the expected shift did not appear. The result was deeply unsettling for classical physics. It was not loud or dramatic, it was almost worse than that. It was quiet, precise, and stubborn. The ether, which had seemed like a sensible explanation, began to disappear from serious physics. Then, in 1905, Albert Einstein proposed the special theory of relativity. Einstein began with two principles. The first was that the laws of physics are the same for all observers moving at constant velocity. These are called inertial observers. The second was that the speed of light in a vacuum is the same for all inertial observers, no matter how the light source or observer is moving. This sounds simple, but it changes almost everything. In ordinary life, speeds add together. If you walk forward inside a moving train, someone standing beside the track combines your walking speed with the speed of the train. If you throw a ball forward from that train, its speed relative to the ground is affected by the train's motion. This is how common sense expects the world to work. Light does not follow that rule. If a spaceship moving very fast shines a beam of light forward, an observer still measures that light travelling at the same speed of light. Not the speed of light plus the spaceship's speed. Not the speed of light minus the observer's speed. Just the speed of light. Something had to give, and what gave was the old belief that space and time are absolute. Einstein showed that observers moving relative to each other can disagree about lengths, durations, and simultaneity, while still agreeing on the laws of physics and the speed of light. Time was no longer a single universal background flowing identically for everyone. Time became linked to motion. The clearest example is time dilation. A moving clock is measured to run slow relative to an observer. This does not mean the clock is badly made. It does not mean the hands are sticky, the gears are sulking, or the battery needs replacing. It means that time itself is measured differently for objects in different states of motion. At everyday speeds, this effect is tiny. Walking to the shop does not make you noticeably younger than someone who stayed at home, which is a shame, because it would make light exercise much more popular. But as speeds approach the speed of light, time dilation becomes dramatic. A clock moving very fast can record less elapsed time than a clock that remains behind. The spoken form of the time dilation equation is: the time measured by a moving observer is equal to the stationary time divided by the square root of 1 minus the speed squared divided by the speed of light squared. This equation expresses a startling idea. Time depends on motion. There is no single master clock shared by the entire universe. Special relativity also introduced the relativity of simultaneity. Two events that appear to happen at the same time for one observer may not happen at the same time for another observer moving differently. This is not a trick of perception. It is not caused by delayed information in the ordinary sense. It is built into how space and time fit together when the speed of light is fixed. Einstein often explained this with thought experiments involving trains and lightning. Imagine lightning striking both ends of a moving train. An observer standing beside the track may judge the strikes to be simultaneous, but an observer on the train is moving toward the light from one strike and away from the light from the other. Because both observers measure light as travelling at the same speed, they can disagree about whether the two strikes happened at the same time. This disagreement reveals something profound. There is no universal now that every observer must share. The twin paradox makes the same lesson more personal. One twin stays on Earth, while the other travels through space at extremely high speed and then returns. The travelling twin can come back younger than the twin who remained on Earth, because less time has passed along the traveller's path. This is not a true contradiction. The travelling twin changes direction, accelerates, and shifts between inertial frames, so the two twins do not have symmetrical journeys. Still, the result is astonishing. Two people can reunite after experiencing different amounts of time. Einstein did not prove that time is unreal. In fact, he made time more physically serious than ever. Time could stretch. It could differ between observers. It could no longer be separated from motion, light, and measurement. So the question of whether time is real became harder, not easier. Time still exists in the equations. Clocks still measure it, bodies still age through it, but it is not the universal independent flow that Newton imagined. It is stranger than common sense expects, flexible, observer-dependent, and deeply woven into the behaviour of light itself. Einstein had already made time less universal than common sense expected, but the next step made the picture even stranger, because special relativity did not merely show that clocks can disagree. It suggested that space and time are not truly separate ingredients of reality. They are different aspects of one deeper structure. In 1908, the mathematician Hermann Minkowski gave Einstein's special relativity its most powerful geometric form. Minkowski had once been one of Einstein's teachers, and he saw that the strange effects of relativity could be understood more clearly if space and time were joined together. Instead of thinking of the universe as three-dimensional space evolving through a separate flow of time, Minkowski described a four-dimensional structure called space-time. In this picture, space and time are woven into a single geometric framework. That may sound abstract, but the basic idea is gentle enough. In ordinary space, an object can be located using three directions: left and right, forward and backward, up and down. But an event needs more than a place. It also needs a time, a firework exploding, a clock ticking, a star emitting light. A door closing or a cup landing on the floor is not fully described by saying where it happened. We also need to say when it happened. So an event in space-time is like a location in a four-dimensional map. It has 3 dimensions of space and 1 dimension of time. The event does not just happen somewhere, it happens somewhere and somewhen. This was a major change in how physicists imagined reality. Before relativity, it felt natural to think of space as the stage and time, as the flow in which things changed on that stage. But Minkowski's interpretation suggested that different observers moving relative to one another are not simply disagreeing because one has made a mistake. They are dividing the same four-dimensional reality into space and time in different ways. One observer may measure a certain distance between two events. Another observer, moving differently, may measure a different distance and a different duration. Special relativity allows this, but something deeper remains consistent. That deeper quantity is called the space-time interval. The space-time interval is a combination of the separation in space and the separation in time between two events. Different observers may disagree about the spatial distance and the time duration separately, but they agree on the space-time interval. It is the part of the geometry that stays fixed beneath their different measurements. A simple comparison is a shadow, though it is only a comparison. A 3-dimensional object can cast different 2-dimensional shadows depending on how it is turned toward the light. The shadows may change shape, but the object itself has not changed. In a similar spirit, observers moving differently can slice space-time into space and time differently, while the underlying space-time relationship remains the same. The analogy is imperfect, but it helps reveal the point. Relativity is not just about confusion between observers. It is about a deeper structure they are all describing from different angles. This is where the block universe enters the story. The block universe is an interpretation of relativity also known as eternalism. It suggests that space-time may be understood as a complete 4-dimensional whole, where past, present and future are all part of the same structure. In this view, the present moment is not physically privileged in the way it feels to us. The past does not vanish into nothing, and the future is not simply absent. Instead, all events may belong to the full space-time block. This does not mean we experience all moments at once. We clearly do not. We experience waking up, getting older, remembering yesterday, and wondering what tomorrow will bring. We live along a path through space-time, and our minds arrange that path into the familiar feeling of passage. But eternalism suggests that the whole path may exist within space-time, rather than being created moment by moment by a moving universal present. It is important to be careful here. The block universe is not a laboratory result in the simple sense. No one has placed the universe on a table, tapped it gently, and confirmed that it is definitely a block, which would be difficult for several reasons, including the shortage of tables large enough. The block universe is an interpretation encouraged by the structure of relativity, especially by the loss of universal simultaneity. The equations of relativity are extremely well tested. The philosophical meaning of those equations is where the debate begins. The difficulty comes from the ordinary feeling that time flows. In daily life, the present feels special, the past feels fixed, the future feels open. We do not feel like static parts of a four-dimensional pattern. We feel like beings moving through a changing world. We make choices, wait for outcomes, remember what has happened, and watch events unfold. The block universe challenges that feeling. If all events in space-time are equally real, then time may not flow in the deepest physical sense. The entire history of reality may simply exist as a four-dimensional structure. What we call the passage of time may be connected to consciousness, memory, entropy, and the direction along which physical records accumulate. This is why the idea has troubled philosophers and physicists for more than a century. J.M.E. McTaggart argued that time, as we ordinarily understand it through past, present, and future, contains deep conceptual problems. Later thinkers such as Hugh Price explored how the direction of time in physics may be tied to our perspective within the universe rather than to a simple built-in flow. These debates can become philosophical, but they remain close to physics because relativity itself makes the old idea of one shared present difficult to defend. So is time real in Minkowski's space-time? In one sense, yes. Time is part of the geometry of the universe. Clocks measure it. Motion affects it. Observers use it to locate events. But in another sense, the flowing time we feel may not be fundamental. The present may not be a cosmic spotlight sweeping across existence. It may be a feature of how conscious systems experience their path through space-time. Minkowski did not remove time from physics. He gave time a deeper and stranger home. Time became part of space-time, joined to space in a four-dimensional structure that all observers describe in their own way. And the story was not finished, because Einstein's later theory of general relativity would make space-time even more physical. It would not merely be the map of events, it would bend, stretch, and curve in the presence of mass and energy. Einstein's special theory of relativity had already weakened the old idea of a universal clock. But general relativity went further. It did not simply say that motion changes how time is measured. It said that gravity changes time as well. In 1915, Albert Einstein presented his general theory of relativity, a new theory of gravity. In Newton's picture, gravity was a force pulling masses toward one another across space. Earth pulled on the moon. The sun pulled on Earth. Every object with mass attracted every other object with mass. It was powerful, elegant, and extremely useful. But Einstein described gravity in a different way. Gravity was not a conventional force acting through space. It was the curvature of space-time itself. Mass and energy shape space-time, and objects move by following the curved paths that space-time makes available to them. A planet orbiting the sun is not being tugged by an invisible rope. It is moving through curved space-time, following the natural path created by the sun's mass and energy. This changed time again, because space-time includes time. If gravity curves space-time, then gravity also affects the ticking of clocks. This effect is called gravitational time dilation. A clock deeper in a gravitational field ticks more slowly, compared with a clock farther away from the source of gravity. A clock near Earth's surface ticks slightly more slowly than a clock high above Earth. The difference is tiny in ordinary life, but it is real. It has been measured many times, and it is not a flaw in the clocks. It is a feature of time itself in curved space-time. A useful way to imagine it is to think of gravity not only as something that bends the paths of objects, but also as something that changes the rhythm of time. Near a massive object, time runs a little slower. Farther away, where gravity is weaker, time runs a little faster. This is not because clocks are tired near planets, although one could forgive them. It is because the geometry of space-time is different. The effect becomes important in technologies we use every day. The global positioning system depends on satellites orbiting high above Earth. Those satellites carry extremely accurate atomic clocks. Because they are moving relative to clocks on the ground, special relativity makes their clocks tick slightly slower. But because they are farther from Earth's gravitational field, general relativity makes their clocks tick faster. The two effects do not cancel exactly.